Hello everyone! In this video we'll be working through a very specific example called the magic square. And this example will allow us to see how two-dimensional arrays can be used to solve problems, how we can get information into a two-dimensional array, and some basic problem-solving steps. Problem solving is usually built on this idea of analysis and synthesis. In analysis, we break down our program or decompose it into the major tasks or steps that need to be completed. Then we solve each of those little mini problems or tasks and synthesize them into a general solution. When it comes to programming, the trickiest part is usually identifying the major tasks to be completed. Once we have all of those tasks, we can then complete them one by one. There's two major schools of thought. We can do smaller and easier tasks first, or we can complete them in order if the problem has a general sequential order to it. Regardless, we should test each task as it's completed so that we know that once a problem's been solved, it's not going to be affected by other things that we add to the program. So we're going to put these ideas to work as we solve the magic square problem. A magic square is an n by n square of values that contains all of the numbers from 1 to n squared exactly once, and each row, column, and diagonal add up to this value, n times n squared plus 1 all over 2. The smallest n value we can have is 3, which is what we'll be basing our example on. A 3 by 3 magic square has to contain all of the values from 1 to n squared, so from 1 to 9. And each row, column, and diagonal has to add up to 15, n times n squared plus 1 all over 2. So the problem that we're trying to solve is how can we write a program that identifies whether or not a 3 by 3 square of integers is, in fact, a magic square. So to solve the problem, we know that our first step is to break this down into smaller pieces. What are the major tasks that need to be completed in order to figure out if something is a magic square? Our first step is to get the square into the program. We're going to need a two-dimensional array for our 3 by 3 square. We can then get the input from the user or from a file, using scanf or file scanf respectively. We know we need to check for all of the numbers from 1 to n squared, so we're going to be looking for all the numbers from 1 to 9. Similar to our mode example, we'll use a frequency array to make sure that they appear once and only once. Then we'll need to check the sums of the rows, columns, and diagonals to make sure they add up to the appropriate value. Here's the example that we're going to be working with. We've got a square of numbers. We're going to read them into our file and build a series of code segments that will solve the problem. We'll take it one step at a time. We've built an input file that has all of the same data, 816.357.492, and called it square.txt. And this way we can get information from the file, but we'll also look at how we can get it from the user. For right now, we're going to be working with a 3 by 3 magic square, but we're going to define this as a constant so that we can expand it to bigger sizes later on. So remember, our first major step was getting the information into our program. We're going to need to declare a two-dimensional array and get information either from the user or from the file. A magic square is made of integers, so integer is going to be our data type for a two-dimensional array. So we're going to call it square. This is what's going to store our square for the program, and we'll check to see if it's a magic square. We know that we're also going to need a frequency array. So we can build a one-dimensional array for frequency. Remember, we're going to need all of the numbers from 1 to n squared, in this case psi squared. And just like our mode example, we want to have that extra 1 so that we can use indices 1 through n squared to hold the frequency of those numbers. And we'll skip over 0. There's a couple of other things that we know we're going to need. Since we're working with a two-dimensional array, we'll need two counters, I and j. We're going to be calculating some sums later on, so we'll need a sum variable. And then I'm also going to build a flag that's called check square. So this is one that will tell us whether or not our square is a magic square. We're going to start by assuming that it is. That's why we're starting with 1 for check square. 1 represents true. We're going to start by assuming that our square is a magic square. And as we test it, if we find anything to disprove that, we can change check square to 0. We can ask the user to supply values for our magic square and place them into the two-dimensional array using this set of nested for loops. I want the user to enter values for the square. We're going to scan them in. We're storing integers, so we're going to use the %d code and store them in our square in the ith row and the jth column. Once we've got information from the user, we're going to print it back out just to make sure that what we have is the same as what they entered. Okay, we'll test this out real quick using the same values that we're going to read from the file later on. So it says enter the values. We're going to do the ones from the file. And then when we print out the square, it looks exactly the same as the one in the file. So that's how we can get information from the user, same as we always do with our scan format function, matching the data type to the type that we're using for our two-dimensional array, and then make sure we're placing it in the correct location, in this case the ith row and the jth column. So we'll leave that there so we can look at it again if we need to. We also want to be able to get information from a file. We're going to create a file pointer and open our square.txt input file, this one over here, in read mode so that we can try and get the information without having to type in all 9 numbers. This way we don't have to prompt the user. We're just going to read the information directly from the file into the array. We'll use our file scan format function to read from the input file an integer and store it into the ith row and the jth column of the array. And we're going to leave this printout so that we can make sure that that worked. So that now when we're reading from the file, the contents of the array in memory are still the same as the ones from our file. So now we're ready to process it and see if it is a magic square. Alright, so our next major step was the frequency. There's a couple of steps to checking for the frequency, so sometimes we need to take these tasks that we've identified for solving the problem and break them down into even smaller tasks. When it comes to checking for the frequency, we need to initialize the frequency array, then populate it with actual values, and then check the values to make sure that each one is equal to 1. So we've seen each value once and only once. So when we're setting up our frequency array, remember it's a one-dimensional array, so we're going to only have one for loop, and we're going to be checking the actual length of that array. So when we set up our control, we want to make sure we match the length of the array. We're going to initialize all the values to 0, and then we will traverse the square, just like we did with mode, adding values to the frequency array as we go. So since we're traversing the square, we're back to using our nested for loops so that we can go through the two-dimensional array. We can also check to make sure our values are with the appropriate range. We know we're looking from values from 1 to n squared, or 1 to 9 in our case. So if we find values that aren't in that range, then we know that it's not going to be a magic square. So if the value we're currently looking at is not between 1 and n squared, then we know that we don't have a magic square. And we're going to set our flag, called check square, to be false or 0. And then we'll go to the frequency array at our current value and increment its frequency by 1. So if we're at I and j are both 0, we know that's the first square of our two-dimensional array, which is equal to 8. So we would go to the 8th spot of the frequency array and say that we've seen 1, 8. Once we have all of our frequencies, we can now check to make sure that they're all equal to 1, 1 and only 1. So we're going to traverse the frequency array using its length and say that if that frequency is not equal to 1, then this is not a magic square, because either one number appears too many times or a number doesn't appear at all. We need to make sure we start at 1 in this case, because the 0th spot of the array should be equal to 0. There should not be any zeros in our square. Okay, so we've completed one total task. We have our frequency. We're going to make sure that it's working. We're going to test it, and we're going to change our input a couple times so we can verify that it's working. If check square is still equal to 1 at the end of the program, then we will have concluded that it's a magic square. And if not, we'll have concluded that it's not a magic square. So we're going to go ahead and build those final answers in so that we can test it and see how it goes. So for right now, the only task we have completed is the checking for the frequency. And it says based on the frequency, we would say this is a magic square. And so that's because each number appears once and only once from 1 to n squared. It's got all of the values from 1 to 9, and each one appears only once. So if we want to make sure that it's working correctly, we're going to change one of our values and make sure it correctly says that it's not a magic square. So now when we run it with the new data, we can see that this square matches this one. It's now not a magic square because we don't have all of the values from 1 to 9, and they don't all appear only once. So we can conclude that our frequency portion is working correctly, and we can now move on to the next task. We're also going to put that back to normal so we can use it again later. Okay, so our next major task is to check the sum of the rows. So we're going to need to go through each row and calculate the sum of each row to make sure it all adds up to the correct value. So we're going to set up an outer for loop that runs through the number of rows. For each row, we want to calculate the sum. So at the beginning of each row, we're going to set sum to 0. Then we'll go across the row and add each value in that row to the sum. And once we have the sum, we're going to check it against the value it's supposed to be, which is size times size squared plus 1 all over 2. And if it's not equal to the correct value, then it must not be a magic square, and we're going to set our flag to 0 to represent false. So now we're going to check to see that this part is working correctly. It's telling us that it's currently a magic square, which now means that both the frequency and the sums of the rows all check out. We can double check that really quick. We know that with a 3 by 3 square, we expect all of them to add up to 15. So we'll make sure that each of these rows add up to 15, and since they do, we know that our program is operating correctly. If we want to test it, we'll also send it a false case. We don't want to mess with the frequency because we don't want frequency giving us what's called a false negative. So we're going to preserve the frequency but change the rows. So that if we give our program this input, it should now correctly tell us it's not a magic square because these rows do not add up to 15. We'll store our input file as we start the next task. We've got the rows. Now we need to check the sums of the columns. So this time we're going to set our outer loop to go in the column direction. And for each column, same as each row, we're going to reset sum to 0 and then go down the column, adding each value in the column to our sum. So this time, J stays the same, and I changes so that we go down each column instead of across each row. And then, if our resultant value is not equal to size times size squared plus 1 all over 2, then it must not be a magic square. Okay, so that's another task down, and now we need to check this one to make sure that it's working correctly. We're going to run it as it currently stands. Now it still thinks it's a magic square based on frequency, rows, and columns. We've already checked the frequency and the rows, so we know that's correct. So now we need to double check the columns and make sure they all add up to 15. And since they do, we know that it's still a magic square and we're still getting the right answer from our program. And now we'll test a false case, keeping everything else to the same. So the frequency is still the same, the rows still add up to the right numbers, but now the columns should not. So if we test it with this input, our program also correctly identifies when it's not a magic square. So it's still working great. So our final task is to check the diagonals. And there's two. There's a forward diagonal and backward diagonal. We need to be able to check 8, 5, and 2, and 4, 5, and 6 in this particular case. It might be helpful for us to look at the indices for each value. 8's at 0, 0. 1's at 0, 1. 6 is at 0, 2. Remember, row first, then column. So the 0th row. 3 is at 1, 0. 5 is at 1, 1. 7 is at 1, 2. So the 1 row, columns 0, 1, and 2. 4 is at 2, 0. 9 is at 2, 1. And 2 is at 2, 2. So if we want to add this diagonal, if we want to add 8, 5, and 2 together, we want to add the values at 0, 0, 1, 1, and 2, 2. So for the diagonal, just like with the rows, we want to start our sum at 0. Then we're going to go across the diagonal and add each value to the sum. So we want to add the values at 0, 0. When I is equal to 0, that'll be 0, 0. When I increments to 1, that'll be 1, 1. And when I increments to 2, that'll be 2, 2. So that'll get our values from that first diagonal. And if those don't add up to the correct sum, then it must not be a magic square. Okay, so now it's time to do the other diagonal. This one's a little bit more complicated, so we're going to go back and examine these values again. We need to add 0, 2, 1, 1, and 2, 0 together. One of the indices starts at 0 and counts upwards each time. So just like a normal for loop, we would start at 0, then go to 1, and then to 2. This other value starts at 2 and counts down. So for the diagonal, we're looking for our counter, and the other one is size minus counter minus 1. So on our first iteration, this would be 0. This would be size minus 0 minus 1, which would be 2. On our next iteration, this will be 1. This will be size minus 1 minus 1, which will be 1. And on our final iteration, this will be 2. This will be size minus 2 minus 1, which will be 0. So now we'll take this and turn it into code that will check that diagonal. We use our counter, and we want to add to sum each value in the diagonal, which we can find by using I, and size minus I minus 1. And if, of course, our sum is not the value that it should be, then it must not be a magic square. But if it passes all of our tests and check square is still equal to 1, then we'll print out it is a magic square. If it fails any one test, it's not a magic square, and we'll print out that result. Now let's check this final solution. It's telling us that it's still a magic square, so we'll double check it real quick. We want to make sure that 8, 5, and 2 add up to 15, 4, 5, and 6 add up to 15, and since they do, this is a magic square. Our program has correctly identified it, and we just want to make sure that if we give it an incorrect square, it's still going to work. There isn't really a way that we can mess with the diagonals without also messing up the row and the column sums. So what we're going to do is we're going to comment those out for right now. We already know that they work, so we don't need them to give us a false negative in this case. We just want to check the diagonal portion. So now we can change the diagonals and make sure that our program recognizes when it's not a magic square based solely on diagonals. It says that it's not a magic square, which is correct because we changed these two values and they are no longer adding up to 15. Okay. Alright, so that's our magic square example. We've built a program that correctly recognizes when we've input a magic square. We've got one that can easily be modified to check a program that has a bigger square. We just have to change the value of size and modify our input file so that it has a 4x4 or even a 5x5 or larger. I hope you found this useful for dealing with two-dimensional arrays. In our next chapter, we'll start looking at functions, which will help us even further modularize our programs and help with these problem-solving tasks. We'll see you then.